July 3, 1944. Biak Island, Dutch, New Guinea. Captain Thomas McGuire watches a civilian in his 40s climb into the cockpit of a P-38 Lightning, and he knows this is either brilliance or madness. The man's name is Charles Lindbergh. He has no military rank, no combat authorization, and according to every pilot's manual in the 5th Air Force, he's about to do something that will destroy 2 Allison engines before they clear the runway. The mission brief was simple. Escort dive bombers to Japanese positions on WWII Island, 280 miles north, 6 hours round trip. Every P-38 pilot knows the fuel mathematics by heart. Standard cruise settings: 2,200 RPM, auto-rich mixture, manifold pressure at 34 inches. Result: 6 hours maximum endurance with a 30-minute reserve. After that, you swim. But Lindbergh claimed he could fly 9 hours on the same fuel load. The squadron engineering officer had listened to Lindbergh's proposal the previous evening and declared it suicidal. "You want us to run 1,600 RPM? That's below minimum continuous power. The engines will carbon up, the plugs will foul. And you want to increase manifold pressure while dropping RPM? That violates every principle of engine management we've ever been taught." Lindbergh had smiled. "The principles you were taught are designed to prevent inexperienced pilots from damaging engines through ignorance. I'm proposing we use specific fuel-to-air ratios that extract maximum energy per gallon while maintaining thermal limits. Your Allison V-1710s can handle it. And if you're wrong, then I have a spare engine to get home." Now, at 0530 hours, with rain hammering the pierced steel planking of the runway, Lindbergh runs through his pre-flight checks, while McGuire's Element forms up behind him. The radios crackle. Weather over target is marginal. The mission could be scrubbed. But Colonel Charles MacDonald, commanding officer of the 475th Fighter Group, makes the call. "Satan's Angels, you are go for takeoff." Lindbergh's P-38 rolls forward. The twin Allisons spool up, counter-rotating propellers biting into humid air. McGuire watches the manifold pressure gauges through his canopy as Lindbergh's aircraft accelerates. 30 inches. Standard takeoff power. The Lightning lifts cleanly, gear retracting, and turns north toward the combat zone. At altitude, Lindbergh does exactly what the manuals say will fail. He reduces propeller RPM to 1,600. He sets both mixture controls to auto-lean. He increases manifold pressure to 32 inches. The engines should protest. They should overheat, detonate, or simply quit. Instead, they settle into a deep, economical rumble that every pilot in the formation can hear is different. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The fuel flow gauges tell the story. Lindbergh's P-38 is burning 40% less fuel than anyone else in the formation. Over WWII, they strafe Japanese barges, drop ordnance on supply dumps, and engage in a brief dogfight with 3 Nakajima Ki 43 Oscars. 7 hours after takeoff, they return to Biak. Lindbergh's aircraft still has 90 gallons remaining. The rest of the squadron lands with minimums, some with warning lights glowing amber. In the debriefing tent, the pilots crowd around Lindbergh. "How?" The civilian pulls out a notepad and begins sketching fuel consumption curves, explaining brake-specific fuel consumption, volumetric efficiency, and the relationship between engine speed and thermal load. Most of it sounds like engineering theory until he translates it into pilot language. You've been taught that high RPM protects engines. That's partially true for combat power, where you need maximum responsiveness. But in cruise, high RPM just spins the propeller faster than necessary to maintain airspeed. You're wasting energy accelerating air that doesn't contribute to thrust. Lower RPM with slightly higher manifold pressure gives you the same power output with significantly better fuel economy. But the manuals. The manuals were written for the lowest common denominator. They assume pilots don't understand engine management, so they provide settings that are safe, even if misused. I'm not asking you to violate thermal limits or stress components. I'm asking you to use the engines efficiently within their operational envelope. A pilot from the 431st Fighter Squadron raises his hand. Mr. Lindbergh, with all respect, who the hell are you to rewrite Allison's specifications? Lindbergh's expression doesn't change. I'm the man who flew a single-engine aircraft 3,600 miles across the Atlantic in 1927 by managing fuel consumption precisely enough to arrive with 85 gallons remaining. I'm the technical advisor who helped Ford troubleshoot B-24 production at Willow Run. I'm the consultant who taught Corsair pilots how to double their combat radius, and I'm the only person in this tent who just flew your mission profile with enough fuel left to fight for another hour. So I suppose I'm qualified. The room goes silent. Over the next 2 weeks, Lindbergh flies with every squadron in the 475th Fighter Group. He demonstrates his techniques repeatedly. Pilots watch their fuel gauges with disbelief, as missions that should drain tanks to minimums leave substantial reserves. The group's effective combat radius extends from 570 miles to 750 miles. Suddenly, Japanese bases that were previously untouchable come within range. The implications are staggering. But to understand why Lindbergh's fuel management breakthrough mattered so profoundly, and why it represented a complete reversal of 5th Air Force doctrine, you have to go back 18 months earlier, to the crisis that nearly lost the Pacific War. January 1943. The United States Army Air Forces faces a brutal mathematical problem. Japanese forces control a defensive perimeter stretching from the Solomon Islands through New Guinea to the Dutch East Indies. American bombers must strike these positions to support MacArthur's island-hopping campaign, but bomber formations without fighter escort are slaughtered by Japanese interceptors. The P-38 Lightning is the only American fighter with sufficient range to escort bombers deep into Japanese territory. Its twin-engine design provides redundancy over vast ocean distances. Its centerline armament delivers devastating firepower. Its speed exceeds 400 miles per hour. The problem is fuel. A P-38F carries 410 gallons of internal fuel plus 2 external 75-gallon drop tanks. Total, 560 gallons. At standard cruise settings, that fuel provides approximately 6 hours of flight time. Subtract 30 minutes for takeoff and climb. Subtract 30 minutes for combat reserve. Subtract 30 minutes for approach and landing. Result, 4.5 hours of usable mission time. At cruise speed of 290 miles per hour, that's a combat radius of approximately 520 miles. Anything beyond that is unreachable. Japanese commanders know this. They position critical targets 550 miles from American bases. Just beyond range, just beyond reach, the 5th Air Force tries everything. Engineers design larger drop tanks. 108-gallon tanks become available in February 1943, extending range to 585 miles. It helps, but it's not enough. 330-gallon tanks are developed for ferry missions, but they're too large and draggy for combat operations with the weight of full fuel. Pilots push their aircraft to the limits. They fly at minimum safe altitude to reduce drag. They lean mixtures until engines run rough. They calculate fuel burns down to single-gallon margins. Men die when calculations are wrong. P-38 seconds ditch in the ocean, 30 miles from base, fuel exhausted, pilots rescued by Catalina, flying boats if they're lucky, sharks if they're not. The statistics are unforgiving. Between January and June 1943, the 5th Air Force loses 42 P-38 seconds to fuel exhaustion. Not combat, not mechanical failure, simple arithmetic. The Japanese defensive perimeter holds because American fighters cannot reach far enough to break it. Admiral Isoroku Yamamoto, architect of the Pearl Harbor attack and commander of the Japanese combined fleet, understands this perfectly. In April 1943, he plans an inspection tour of forward bases in the Solomon Islands. His staff calculates that American fighters cannot reach the route from their bases on Guadalcanal. The flight is 435 miles each way, beyond P-38 combat radius, safe. American intelligence intercepts Japanese communications detailing Yamamoto's itinerary. The opportunity is unprecedented. Kill Yamamoto, and Japanese naval leadership collapses. But the mission is impossible. The target is too far. Major John Mitchell, commanding the 339th Fighter Squadron, studies the numbers obsessively. 435 miles to interception point. Combat time over target, 10 minutes maximum. Return flight, 435 miles. Total, 880 miles round trip plus combat reserve. His P-38Gs cannot do it, unless Mitchell requests every 330-gallon drop tank in the theatre. Maintenance crews jury-rig mounting hardware designed for smaller tanks. The result is ungainly. Each P-38 carries 165 gallons under one wing and 330 gallons under the other. Asymmetric, draggy, marginally controllable, but mathematically sufficient. On April 18, 1943, 16 P-38 seconds launch from Guadalcanal at 07:10 hours. They fly at 50 feet above the ocean to avoid radar detection. Navigation is dead reckoning over featureless water. No landmarks, no radio navigation aids. Celestial navigation with a sextant while flying formation at wave-top height. One navigational error means missing the intercept entirely. 435 miles later, at 09:34 hours, Mitchell's formation arrives at the interception point within 60 seconds of Yamamoto's bombers. The Americans climb, drop external tanks, and attack. 2 Mitsubishi G-4M Betty bombers go down in flames. Yamamoto's aircraft crashes in the jungle. The admiral is found dead in his seat, killed by 50 caliber rounds that entered through the aircraft's left rear fuselage. The mission succeeds. But barely. 3 P-38 seconds run critically low on fuel during the return flight. One ditches 50 miles from Guadalcanal, pilot rescued. The fuel margins were measured in minutes. 5 minutes more combat time would have meant 5 fewer aircraft returning. The Yamamoto mission proves that P-38 seconds can reach extreme distances with massive drop tanks and perfect planning. But it's not sustainable. You cannot run every mission with 330-gallon tanks and zero margin for error. The 5th Air Force needs a solution that works for regular combat operations, not just special missions planned for weeks. Engineers attack the problem from every angle. Lockheed redesigns the P-38's intercooler system in the P-38J variant. The original design placed intercoolers in the wing leading edges, requiring long ducting that created vulnerability and complexity. The new design moves intercoolers to chin-mounted radiators beneath each engine. This frees up wing leading-edge space for 55-gallon fuel tanks, adding 110 gallons to internal capacity. The modification works. P-38J models entering service in August 1943 carry 520 gallons internally, plus 2 external 108-gallon tanks, for a total of 736 gallons. That's 176 more gallons than the P-38F. It should provide an additional hour and a half of range. But it doesn't. Pilots report fuel consumption remains stubbornly high. The extra fuel capacity extends endurance from 6 hours to 7 hours, not the theoretical 8.5 hours. Something is wrong with the fuel management doctrine itself, and no one can figure out what. The answer walks off a transport aircraft in June 1944, wearing civilian clothes and carrying a technical manual for the Allison V-1710 engine. Charles Lindbergh has come to teach the 5th Air Force something they think they already know: how to fly their own aircraft. The initial reaction is skepticism bordering on hostility. Who is this civilian to tell combat pilots how to operate fighters? These men have flown hundreds of missions. They know their aircraft intimately. They've lost friends to fuel exhaustion and combat losses. They've pushed P-38 seconds to every conceivable limit. What could a 42-year-old former airmail pilot possibly teach them? Lindbergh doesn't argue. He flies. He joins every mission profile the squadrons run: bomber escort, fighter sweep, ground attack, reconnaissance. And every single time, he returns with dramatically more fuel remaining than anyone else in the formation. The breakthrough isn't a mechanical modification. It's not a new component or a redesigned fuel system. It's the realization that official engine operating procedures are written for institutional protection, not operational efficiency. The Allison engine manual specifies 2200 RPM minimum cruise to prevent pilots from operating in regions where improper mixture control could cause detonation. It's a safety buffer. But Lindbergh understands the thermodynamics well enough to operate outside that buffer safely. The key is brake-specific fuel consumption, the amount of fuel required to produce 1 horsepower for 1 hour. This varies with RPM and manifold pressure. At high RPM and low manifold pressure, you're spinning the engine fast but not producing much power per revolution. At low RPM and high manifold pressure, you're extracting more energy per revolution, reducing parasitic losses from friction and pumping. Lindbergh's settings: 1600 RPM, 30 to 32 inches of manifold pressure, auto-lean mixture. This combination produces approximately 65% power, sufficient for cruise flight, but at a brake-specific fuel consumption nearly 40% lower than standard settings. The engines run cooler because combustion events occur less frequently. Thermal stress actually decreases. But there's a catch. Running low RPM with lean mixture requires constant attention to cylinder head temperatures and exhaust gas temperatures. If manifold pressure goes too high, or if the mixture leans too much, detonation can destroy an engine in seconds. The official procedures prevent this by keeping RPM high enough that even careless mixture control stays safe. Lindbergh's technique requires skill and attention. The 5th Air Force pilots have both. They're experienced, disciplined, and desperate for any advantage. Lindbergh spends 2 weeks teaching them how to monitor engine instruments, how to adjust mixture for changing altitude and temperature, how to recognize the early signs of detonation, and how to recover if parameters drift outside safe ranges. The results are transformative. Missions previously limited to 6 hours now run 8 hours comfortably. Combat radius extends from 570 miles to 750 miles, some pilots reporting even longer ranges. Japanese bases at Balikpapan, Samarinda, and Tarakan, previously untouchable, suddenly come under regular attack. On July 28, 1944, Lindbergh participates in a bomber escort mission over Seram. During the return flight, a Japanese Sonya observation aircraft appears below the formation. Lindbergh breaks formation, dives, and destroys the aircraft with a single burst from his centerline guns. It's his only aerial victory of the war, achieved while technically a civilian. General Douglas MacArthur, Supreme Commander of Southwest Pacific Area, personally commends Lindbergh's contributions. In a theater where every mile of range translates directly to strategic advantage, Lindbergh's fuel management techniques have effectively added 200 miles to every fighter's reach without changing a single component. But the story of how the P-38 became a long-range escort fighter isn't just about Lindbergh's genius in July 1944. It's about 3 years of incremental improvements, desperate innovations, and pilots who pushed inadequate aircraft beyond their design limits because failure meant losing the Pacific War. To understand the full magnitude of what changed, you need to see where it started, with an aircraft that was simultaneously the most advanced fighter in the world and completely unprepared for the war it would fight. February 1937. Wright Field, Dayton, Ohio. The United States Army Air Corps issues Circular Proposal X-608, a specification so aggressive that every major aircraft manufacturer initially considers it impossible. The requirement: a high-altitude interceptor capable of 360 miles per hour at 20,000 feet, with a combat radius of 1,000 miles and endurance of 1 hour at maximum speed. In 1937, no fighter in the world can meet even half these requirements. Lockheed Aircraft Corporation has never built a military aircraft. Every plane the company has produced has been a civilian transport or racing design, but Chief Engineer Hall Hibbard and his young assistant Clarence Kelly Johnson see opportunity in the Army's impossible specification. They propose something radical: a twin-engine, twin-boom fighter with tricycle landing gear, counter-rotating propellers, and turbo-supercharged engines. The Model 22. The Army awards Lockheed a contract for one prototype in June 1937. The XP-38 emerges from Lockheed's Burbank facility in December 1938, gleaming bare metal, looking like nothing that has ever flown. On January 27, 1939, test pilot Lieutenant Ben Kelsey takes it aloft for the first time. The aircraft is astonishingly fast, stable, and powerful. It's also completely unproven. 11 days later, Kelsey attempts a transcontinental speed record. The XP-38 departs Marchfield, California at 11:02 hours on February 11, 1939, 7 hours. And 2 minutes later, including 2 refueling stops, Kelsey approaches Mitchell Field, New York. He's shattered every transcontinental speed record. The landing should be a triumph. Instead, the engines flame out on final approach. Carburetor ice. Kelsey puts the prototype into a golf course 2 miles short of the runway. The aircraft is destroyed. The pilot walks away. The Army could cancel the program. Instead, they order 13 YP-38 service test aircraft. The basic design is too promising to abandon, but it needs refinement. Lots of refinement. The first YP-38 doesn't fly until September 1940. By then, Europe has been at war for a year. France has fallen. Britain fights alone. The urgency is palpable. Production P-38 seconds begin rolling off Lockheed's assembly line in June 1941. The P-38D incorporates self-sealing fuel tanks and armor protection. It carries 4 50-caliber machine guns and 1 20mm cannon, all mounted in the nose for concentrated firepower without convergence issues. The twin Allison V1710 engines produce 1,250 horsepower each, driving counter-rotating propellers that eliminate torque roll. Maximum speed, 395 miles per hour. Service ceiling, 39,000 feet. Range with internal fuel, 750 miles. On paper, it's spectacular. In practice, it has problems no one anticipated. December 7th, 1941. Pearl Harbor burns. America enters the war with exactly 69 P-38 seconds in service. Most are stationed in California for training. A handful deploy to Alaska and Iceland for defensive patrols. The Lightning's first combat comes not in the Pacific, but over Iceland, where a P-38E shoots down a German Focke-Wulf WWII Condor on August 9, 1942. First American aerial victory of the war. But the Pacific theater desperately needs long-range fighters. In January 1942, the first P-38s arrive in Australia. They're immediately converted to F-4 photo reconnaissance variants because there aren't enough pilots trained to fly them as fighters. The reconnaissance Lightnings prove their worth immediately, photographing Japanese positions across New Guinea and the Solomon Islands. But the 5th Air Force needs fighters, not cameras. The P-38F enters service in April 1942 with a critical addition: underwing pylons capable of carrying drop tanks, bombs, or torpedoes. This should solve the range problem. External fuel tanks can extend range dramatically, but there's a catch. The external tanks themselves are in short supply. Manufacturing capacity is limited. Ships carrying tank shipments to the Pacific theater are torpedoed by Japanese submarines. Squadrons receive aircraft without the tanks necessary to use them effectively. Worse, the tactics are wrong. Early P-38 formations fly close escort, staying within 1,000 feet of the bombers they protect. This negates every advantage the Lightning possesses. Its speed becomes irrelevant when crawling along at bomber pace. Its altitude capability is wasted flying at bomber altitudes, and German and Japanese fighters exploit this ruthlessly, diving from above, attacking, and climbing away before the P-38 seconds can respond. In the Mediterranean theatre, P-38 losses are catastrophic. During Operation Torch, the invasion of North Africa in November 1942, P-38Fs engage Vichy French and German aircraft. The results are mixed. Some pilots score multiple kills. Others die in flames, shot down by more experienced Luftwaffe pilots who understand energy tactics better than the Americans. The problem intensifies in Europe. When P-38 seconds begin escorting 8th Air Force bombers over Germany in October 1943, they encounter conditions for which the aircraft is fundamentally unsuited. The European theatre operates at extreme altitudes, 25,000 to 30,000 feet, where temperatures drop to -50 degrees Fahrenheit. The P-38's cockpit heating is inadequate. Pilots suffer frostbite during missions lasting 4 to 5 hours. Some lose fingers and toes to cold injury. The Allison engines fare even worse. European aviation fuel has different chemical properties than American fuel, causing the turbochargers to behave erratically. The intercoolers, mounted in the wing leading edges, overcool the intake charge in extreme cold. Engines detonate randomly. Others refuse to produce rated power. Maintenance crews struggle with failures they've never encountered in training. On November 13, 1943, the 55th Fighter Group launches 48 P-38HS to escort bombers attacking Bremen. At 26,000 feet over Germany, engines begin failing. Not battle damage, not fuel exhaustion. Mechanical failure induced by extreme cold and temperamental turbochargers. 7 P-38 seconds abort with engine problems. 3 more suffer failures, over target and struggle home on single engines. The bombers they're supposed to protect are savaged by Luftwaffe fighters. The 8th Air Force begins questioning whether the P-38 belongs in Europe at all. The P-47 Thunderbolt, with its radial engine and mechanical supercharger, handles cold weather better. The P-51 Mustang, when it arrives with Merlin engines in late 1943, outperforms the Lightning in almost every metric except range. By September 1944, all but one P-38 group in England converts to Mustangs. But the Pacific Theatre tells a completely different story. In the warm, humid air over New Guinea, the Solomon Islands, and the Philippines, the P-38 thrives. The twin-engine design provides redundancy over vast ocean expanses. Pilots know that if one engine fails, they can limp home on the other. Single-engine fighters offer no such safety margin. The psychological advantage alone is enormous. The top American aces of World War II all fly P-38 seconds. Major Richard Bong achieves 40 confirmed victories, all in Lightnings. Major Thomas McGuire scores 38 kills before his death in January 1945. Colonel Charles MacDonald, Lieutenant Colonel Tommy Lynch, and dozens of others become aces flying the twin-boomed fighter. They develop tactics specifically suited to the P-38's capabilities. Diving attacks using superior speed, boom and zoom maneuvers, exploiting powerful engines, and long-range patrols that Japanese fighters cannot match. The Lightning's concentrated nose armament proves devastating. Unlike fighters with wing-mounted guns that require convergence calculations, the P-38's 450 caliber machine guns and single 20mm cannon fire parallel trajectories. What the pilot aims at, the bullets hit. At close range, the firepower is overwhelming. Japanese aircraft, lacking armor and self-sealing fuel tanks, disintegrate under P-38 fire. But even in the Pacific, range remains the limiting factor. Every Japanese retreat pushes airfields farther north and west. American fighters must reach farther to protect bombers and attack enemy positions. The mathematics are relentless. Each additional 100 miles requires approximately 40 more gallons of fuel. Each additional gallon means more weight at takeoff. More weight means more drag. More drag means more fuel consumption. The spiral is vicious. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Engineers at Lockheed work continuously to improve range. The P-38G, entering service in August 1942, increases internal fuel capacity to 410 gallons. The P-38H, arriving in April 1943, adds automatic engine controls and more powerful engines, but range actually decreases slightly due to increased weight and drag. The P-38J, the definitive variant beginning production in August 1943, finally achieves the breakthrough, relocating intercoolers from wing leading edges to chin-mounted radiators frees up space for 55-gallon leading-edge fuel tanks in each outer wing panel. The P-38J carries 520 gallons internally. Add two 108-gallon drop tanks, and total fuel capacity reaches 736 gallons. In theory, this should provide approximately 9 hours endurance. In practice, at standard cruise settings, pilots achieve 7 hours maximum. The discrepancy frustrates everyone. The fuel is there. The aircraft is there. But the endurance isn't. The missing piece is operational doctrine. The Army Air Forces teaches pilots to operate engines at settings guaranteed safe under all conditions. These settings prioritize engine preservation over fuel efficiency. For training purposes, this makes sense. New pilots cannot be trusted to manage complex engine parameters while navigating, communicating, and fighting. Simple, foolproof settings prevent catastrophic errors. But combat pilots aren't students. They're experienced professionals who understand their aircraft intimately. They can handle complex procedures if those procedures offer operational advantage. No one bothers asking whether official settings are optimal, because institutional momentum assumes they must be. The manuals say 2200 RPM minimum cruise. Therefore, 2200 RPM is correct. The logic is circular and unquestioned, until Charles Lindbergh questions it. Lindbergh's background uniquely qualifies him to challenge accepted wisdom. In May 1927, he flew the Spirit of St. Louis from New York to Paris, 3,600 miles over open ocean in a single-engine aircraft with no radio and minimal instruments. The flight required fuel management so precise that errors of 2% would mean ditching in the Atlantic. Lindbergh calculated every variable: engine RPM, manifold pressure, mixture setting, altitude, temperature, wind correction. He arrived at Le Bourget Field with 85 gallons remaining because his fuel calculations were exact. After his Atlantic crossing, Lindbergh became an internationally recognized expert on long-range flight. He consulted with Pan American Airways on trans-Pacific routes. He advised aircraft manufacturers on engine efficiency. He flew experimental aircraft for the military, testing high-altitude performance and maximum range profiles. When World War II began, his isolationist politics made him controversial, but his technical expertise remained unchallenged. In 1942, Lindbergh approached the military, offering his services. His political stance made formal military service impossible, but he could work as a civilian technical consultant. Henry Ford hired him to troubleshoot B-24 Liberator production at Willow Run. Lindbergh spent months on the factory floor, identifying bottlenecks and solving engineering problems that delayed bomber deliveries. His contributions were significant enough that Ford credited him with saving months of production delays. In 1943, United Aircraft hired Lindbergh to work with Chance Vought on the F-4U Corsair. He flew combat missions with Marine squadrons, teaching pilots how to take off with double the Corsair's rated bomb load by managing power settings and takeoff techniques more precisely than standard procedures allowed. Marine commanders reported that Lindbergh's methods significantly increased the Corsair's effectiveness as a fighter bomber. In June 1944, Lindbergh convinced United Aircraft to send him to the Pacific Theater to study P-38 operations under combat conditions. His official role was technical observer. His unofficial role became far more significant. He arrived at Hollandia, New Guinea on June 15th and immediately sought out the 475th Fighter Group, one of the most experienced P-38 units in theatre. Colonel Charles MacDonald, commanding officer of the 475th, initially regarded Lindbergh with polite skepticism. Combat pilots tend to view civilians with caution, even famous ones. But MacDonald agreed to let Lindbergh fly observer missions, with strict instructions to avoid combat. The Lone Eagle was too valuable to lose in a dogfight. Lindbergh's first mission on June 27, 1944, changed everything. Flying as wingman to Major Thomas McGuire, he participated in a strike against Japanese positions on Biak Island. The mission profile was standard, 5 hours total, including combat time over target. When the formation returned to base, every aircraft landed with fuel gauges reading near empty, 30 to 40 gallons remaining, standard for a 5-hour mission. Except Lindbergh, his P-38 still showed 115 gallons. The crew chief noticed immediately. He checked for fuel leaks, suspecting a gauge malfunction. The gauges were accurate. Lindbergh had flown the identical mission profile as everyone else, but consumed 40% less fuel. MacDonald demanded an explanation. Lindbergh described his engine settings: 1600 RPM, 32 inches manifold pressure, auto-lean mixture. The squadron engineering officer declared it impossible. Those settings should cause engine failure within 30 minutes, Lindbergh offered to demonstrate. On subsequent missions, he flew with different elements, showing each squadron the techniques. The results were consistent: same airspeed, same altitude, 40% better fuel economy. Pilots began experimenting cautiously, gradually reducing RPM and adjusting mixture. Some experienced rough running initially, overleaning the mixture or reducing RPM too aggressively. But with practice, they mastered the technique. The transformation happened quickly. By mid-July, the entire 475th Fighter Group operated using Lindbergh's fuel management procedures. Mission profiles that previously required maximum fuel loads now completed comfortably with reserves. The group's effective combat radius extended from 570 miles to over 700 miles. Targets previously unreachable became routine. Other units heard about the results and requested Lindbergh's assistance. He flew with the 8th Fighter Group, the 49th Fighter Group, and the 475th Fighter Group, teaching the same techniques. By August 1944, most P-38 units in the Southwest Pacific area had adopted modified cruise procedures. The impact on operations was immediate and dramatic. Japanese bases at Balikpapan, Borneo, 950 miles from Allied bases, came under regular fighter escort for the first time. Previously, bomber raids on Balikpapan flew unescorted because fighters couldn't reach that far. Now P-38 seconds escorted the entire mission, engaged Japanese interceptors over target, and returned, with fuel to spare. Japanese commanders, accustomed to safe distances protecting their rear area bases, suddenly faced American fighters everywhere. The extended range enabled missions that would have been impossible months earlier. On October 14, 1944, P-38 seconds from the 432nd Fighter Squadron flew an 8-hour escort mission to Balikpapan and back, covering 1,900 miles. This mission would have been categorically impossible using standard fuel management. With Lindbergh's techniques, it became routine. The tactical implications extended beyond simple range. Longer endurance meant fighters could loiter over target areas, waiting for Japanese aircraft to appear. Previously, P-38 seconds had to time their arrival precisely, spending minimal time over target before fuel constraints forced them home. Now they could arrive early, patrol, and wait for opportunities. This shifted the air war dynamic fundamentally. Japanese fighters, accustomed to attacking bombers after escorts departed, now faced continuous fighter cover. Lindbergh flew 50 combat missions during his 2 months in the Pacific Theater. Officially, he was a civilian observer not authorized to engage enemy aircraft. Unofficially, he carried full armament and participated in every aspect of combat operations. On July 28, 1944, during an escort mission over Ceram, he shot down a Mitsubishi Ki-51 Sonya observation aircraft. The kill was witnessed by multiple pilots and recorded in squadron logs, though officially it never happened because civilians don't shoot down enemy aircraft. General Douglas MacArthur personally commended Lindbergh's contributions, noting that the fuel management techniques had effectively increased the combat radius of every P-38 inches theatre without requiring modifications, new equipment, or additional logistics support. It was force multiplication through operational knowledge, and its value was incalculable. But Lindbergh's contribution, while dramatic and immediately effective, represented only the final piece of a much larger puzzle. The P-38's transformation from a short-range interceptor into a long-range escort fighter required years of engineering development, tactical innovation, and operational experience. The fuel management techniques worked because they optimized an already capable aircraft. Without the P-38J's increased fuel capacity, better drop tanks, and refined aerodynamics, Lindbergh's techniques would have provided incremental improvement, not transformation. The full story requires understanding every piece. The engineering evolution from P-38D through P-38 liters, the tactical lessons learned through costly failures in Europe and hard-won successes in the Pacific, the logistics of fuel supply and maintenance across vast ocean distances, and the human factors of pilot training and institutional resistance to change. Each element mattered. Remove anyone, and the end outcome changes. The P-38's journey from promising prototype to war-winning weapon system took 5 years of continuous refinement under the most demanding conditions imaginable. And the final chapter of that journey involves the most dramatic single mission in P-38 history, where fuel management, extended range, and perfect planning converged to kill the man who planned Pearl Harbor. April 18, 1943, Guadalcanal. 16 P-38G Lightnings sit on Henderson Field's pierced steel planking, each loaded with one asymmetric drop tank configuration. 165 gallons under the left wing, 330 gallons under the right. The mission briefing took 3 hours. The target, Admiral Isoroku Yamamoto, architect of Pearl Harbor, commander of Japan's combined fleet. American codebreakers intercepted his travel itinerary. He'll arrive at Bougainville at 09:35 hours, 435 miles from Guadalcanal. Major John Mitchell commands the strike. He's calculated fuel consumption down to individual gallons. The math allows zero margin. Flight time to intercept, 2 hours, 15 minutes. Combat time, 10 minutes maximum. Return flight, 2 hours, 15 minutes. Total fuel required, 540 gallons. Each aircraft carries 560, 20 gallons reserve. In a P-38, 20 gallons provides 12 minutes flight time, 12 minutes between success and swimming. At 07:10 hours, the formation launches. They fly at 50 feet above the ocean, wave tops blurring beneath them, maintaining radio silence. Navigation is pure dead reckoning. No landmarks, no checkpoints. Just compass heading and calculated time. 1 degree error means missing the intercept entirely. At 09:34 hours, precisely on schedule, Mitchell's formation arrives at Bougainville's southwest coast. Climbing to altitude, they spot 2 Mitsubishi G4M Betty bombers escorted by 6 Zeros. Yamamoto's aircraft, the P-38 seconds, drop external tanks and attack. Captain Thomas Lanphier and Lieutenant Rex Barber dive on the bombers. Lanphier's guns tear into the first Betty. It rolls inverted, trailing fire, and crashes into the jungle. Barber attacks the second bomber, hitting it repeatedly. The Betty ditches near the coast. The entire engagement lasts 4 minutes. The P-38 seconds turn for home immediately, fuel gauges dropping. Mitchell's navigation is perfect. They arrive at Guadalcanal with fuel lights glowing. 3 aircraft land with less than 10 gallons remaining, but they all make it. Mission successful. Yamamoto is dead. The Japanese find Yamamoto's body the next day, still strapped in his seat, killed by 50 caliber rounds. His death devastates Japanese naval leadership. Morale collapses. No single officer can replace him. The psychological impact on Japan is catastrophic, but the mission's success depended entirely on fuel calculations that left no room for error. Those calculations represented the absolute maximum capability of the P-38G with available drop tanks. It worked once, under perfect conditions, with perfect planning and perfect execution. It wasn't repeatable for regular operations. 15 months later, Lindbergh's fuel management techniques made such missions routine. What required weeks of planning, special equipment, and desperate fuel calculations in April 1943 became standard procedure in July 1944. The difference was operational knowledge applied systematically across entire units. By war's end, P-38 Lightnings flew over 130,000 combat missions across every theater. They destroyed more Japanese aircraft than any other American fighter. They escorted bombers to Berlin and Tokyo. They photographed 90% of Allied reconnaissance targets in Europe. 7 of the top 10 American aces flew P-38 seconds, accumulating victories that remain unsurpassed. The aircraft's legacy rests on incremental improvements that accumulated into transformation. Better engines, larger fuel tanks, refined aerodynamics, improved tactics, and optimized fuel management. Each advance built on previous advances. No single modification created the long-range escort fighter that changed the war. The combination did. Charles Lindbergh returned to the United States in September 1944. He never spoke publicly about his combat missions. When he died in 1974, his obituaries mentioned his Atlantic crossing but barely referenced his Pacific service. The pilots he trained remembered differently. They remembered the civilian who taught them to extract 9 hours from fuel tanks designed for 6, who showed them that official doctrine wasn't immutable law, who proved that questioning assumptions could save lives and win wars. The P-38 Lightning proved that range wins wars, but range comes from engineering, tactics, logistics, and human ingenuity working together. From Lockheed's engineers who redesigned fuel systems, to mechanics who installed tanks in jungle heat, to pilots who pushed aircraft beyond supposed limits, to one civilian who understood engines better than the manuals. Sometimes the difference between defeat and victory is measured in gallons. Sometimes it's measured in miles. Sometimes it's measured in the courage to question what everyone knows is true. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.